Okay, so let me remind you about induction. So induction sets up, the following sort of framework. So induction. Okay. Remember induction, you say that, induction is about, a predicate and, is it whether or not the predicate is true. So you have a predicate, P of n. P of n. Okay, and what do you do at the first, in the first step of an induction? You say that, you establish that P of 1 is true. Okay. And in the second step of the induction step, you establish that P of n implies P of n plus 1. So this is the fundamental link that you need to prove in the induction step. And what does that do? It sets up this infinite chain. It sets up this infinite chain, which is P of 1 implies P. So for example, for n greater equal to 1, so it sets up this infinite chain. P of 1 implies P of 2, implies P of 3, okay, implies P of 4, implies, and so on. Okay, and then what you do is you go and establish that this guy is true, and then that gives you P of 2, P of 3, P of 4, infinite cascade of implications tell us that all the value, the predicate is true for all values of n bigger equal to 1. So we conclude that P of n is true for all n greater equal to 1. Okay, so that's induction. Okay, let me show you the link between induction and recursion. Okay. So, in recursion, we don't have a predicate. So, in recursion, okay, we have a function, for example, a recursive function. We have this recursive function, f of n. And, here's what we would like to conclude. We would like to conclude that we can compute f of n for all n, in this case, let's say greater equal to 0. Okay. So we could, if we wanted to define a predicate, P of n, which is the claim that f of n can be computed. But instead, let me just show you that, okay, what we've established here is that, we can compute f of 0. Can compute? Yes. Okay. And now I'm going to go back to this recursion and let's see at a high level what is it saying. What it's saying is that, if I can compute f of 0, so I can, if I know f of 0, okay, so if n minus 1 is 0, then I can compute f of 1. In particular, if I know f of n minus 1, I can compute f of n. So in particular, this is saying that if I know f for any value of n, I can compute it for the next higher value of n. Okay? Now I'm going to write that using the same implication notation, even though we're talking about can we compute as opposed to is it true that. So if P of n is true, it implies P of n plus 1 is true. Okay? What this recursion tells us is that if we can compute f of n, okay, then we can compute f of n plus 1 for n greater equal to 0. Okay? Because I can plug in, if I plug in 0 here, I can compute 1. So if n minus 1 is 0, so that means n is 1. So f of 1 is something plus f of 0. So 0 implies 1. 1 will imply 2. So that's what this is saying. That if I can compute f of n, I can compute f of n plus 1 for any n greater than or equal to 0. Okay. And when you think about it, well, this is setting up an infinite chain of can compute implications. Okay. So if I can compute f of 0, I can compute f of 1. And if I can compute f of 1, I can compute f of 2. And if I can compute f of 2, I can compute f of 3. And so on. Okay. And then what the base case does in the recursion, and no surprise, it's called a base case, just as this is called a base case in induction. What the base case does in recursion, it says, I can compute this guy. Okay. And it sets up an infinite cascade of, implications, which say that I can compute 1, 2, 3, 4, and so on. Okay. So now I leave it to you as an exercise to go and prove by induction that the claim that you can compute f of n for all n greater than or equal to 0. Okay. So we can conclude that instead of, the conclusion here is that P of n is true for all n greater than or equal to 1. The conclusion here is that we can compute f of n for all n greater or equal to 0. Okay. So let's do another example of a recursion. So example. Okay. So I'm going to define f of n is equal to, n plus f of n minus 2 for n greater or equal to 1 and 0 for n equals to 0. Okay. So let's try to compute f of n. So let's do it here. So I'm going to put n and f of n. Usual. Let's just try to see what this recursion is doing. Let's tinker a little bit. So we have n and f of n. So n equals 0, 1, 2, 3, 4, 5, and so on. Okay. What's f of 0? F of 0 is 0. Okay. What's f of 1? Okay, f of 1, and that's what's interesting. F of 1 is 1 plus f of minus 1. So it looks like we're making recursive progress, okay, but we overshoot 0. We overshoot 0 and go to minus 1. And then we're going to have to get minus 3 and then minus 5 and so on and so forth. So we cannot compute f of 1. What about f of 2? F of 2 is 2 plus f of 0. But f of 0 we know is 0. F of 0 is 0. So this is 2. F of 3 is going to ask for f of 1, which we can't compute because it's n minus 2. So we can't compute it. F of 4 is going to be 4 plus f of 2. But f of 2 we computed, so that's going to be 6. 5 we won't be able to compute. So it looks like a perfectly good recursion. We have a recursive case, we have a base case, okay? And we are making recursive progress, except we're not quite making recursive progress because when n equals minus 1, we overshoot and then we start going away. So we don't always make recursive progress. Okay, but how could we immediately see that this is, gonna lead to a problem? We can draw the implication links, just like we did for induction. So let's see what the implication links look like for this recursion. What does this say? F of 0, I know. Okay, so f of 0, I can compute, no problem. Okay, but now what it says is that f of 0 will imply f of 2. And in general, f of n gets... You can compute f of n if you can compute f of n minus 2. That means that if I can compute f of n, I can compute f of n plus 2. If I can compute this guy, I can compute this value plus 2. So we have the computable implication that f of n, if it's computable, implies f of n plus 2. Bam! Okay, so we have f of 1, f of 2, f of 3, f of 4, and so on. Okay? And the implication link from 0 goes to 2. From 2, where does it go? It goes to 4. This should remind you of leaping induction. So there's this very tight link between recursion and induction. Okay? And since we can compute f of 0, since we've tipped that domino, we have this infinite cascade of leaping implications that gives you an infinite number of f for which you can compute. Okay? But it's only going over the even numbers. It's not hitting any of the odd numbers. Okay? And that was the same problem we had when we did leaping induction. What's the solution? The solution is very simple. You just need to add one more base case in leaping induction, and the same thing for this kind of a recursion. Because the leaping, if you add this base case, you still have the implications that n implies n plus 2 with respect to what can I compute. So 1 will imply 3. It's just that before, we did not have the base case 1. And 3 will imply 5. And now you have two independent chains that go and say, and together, if you can get both infinite cascades of implications going with my two base cases, now I will have all the values of f of n computable. Okay. So what's wrong here? I need another base case. I could say, for example, f of n is 0 for n equals 0 or 1. And now this becomes the recursive case for n greater or equal to 2. That will fix. I've added two base cases. Just like if I have leaping induction, I need two base cases if it's two leaping induction. There's a tight link between induction and recursion. Okay. So if ever you're wondering, is my recursion valid? You'll have to prove it by induction. Okay. And the basic idea is here that it sets up this infinite chain of implication, and you prove the claim f of n is computable for natural number n or for integer n. Okay. And then you have to prove that claim by induction. Okay. I leave it to you to prove that claim by induction. The basic idea is in these links, and then if the induction is going to work, if the sort of implication setup for induction will work, then the corresponding implication setup for recursion will work. And there are many ways to do recursions, complicated recursions, and each of them, in order to ensure that all function values can be computed, that will be related to the corresponding type of induction, leaping induction, ordinary induction, and so on and so forth. You can even have, okay. All right. So that's this tight link. Let me show you again the resurfacing of this tight link one more time.